Example 5.3, determine the output voltage as well as the output current. So I'm going to solve using 3 different techniques to get this. So I'm going to solve for vout and iout using 3 techniques. I'm going to use source transformations, I'm going to use simple circuits, and then I'm going to use node. So here, the first one is that I'm going to use source transformations. And I'm going to use simple circuits. So the first thing that we want to note here is that here's our circuit right here. So the first thing that I'm going to see here is that note that the 12 volt and 6K are in series. So that's a Thevenin resistance and a Thevenin voltage source. So if I look at between this guy here and this, you could see that these two guys are in series. So I'm going to call this 1, 2, 3, 4, and I'm going to call this resistor 5 because they're all 6K. So now I'm going to do a source transformation right here. So here I go. So now I'm going to look at a source transformation. So I'm going to transform this guy. So I'm going to get 12 divided by 6, which will give me 2 milliamps. So here I go. So I'm going to have a 2 milliamp source going like this. I'm going to have a resistor that's going to be a 6K. And now I have my other 6K. So here's my 6K. And this 6K is resistor 3. Then I have this guy up here, which is my resistor 2. And then I have my op amp. And then, of course, this guy goes to ground. And then I have my output, which is resistor 5. And then I have my other resistor here. And this one's 4. So now you could see here is that I could do another source transformation right here. So if I do this, I could just keep doing more again and again source transformation. So if I do that source transformation, note that I have 6K and 6K in parallel. So that's a 3K. Then I'm going to have 2 times 3, which is going to give me 6. So what this means here is that I'm going to end up with a source now that looks like this here. I'm going to get a 6 volt. And then I have a 3K. So then it connects to the rest of the circuit. So then I have resistor 2 goes to the op amp. So now if I look at this thing, you can see here is that this is resistor 2, this is resistor 4, and this is resistor 5. And so when I'm looking at these, remember, these are all 6K, right? So this is 6K, this is 6K, this is 6K. So do I need to do any more source transformations? I could, because I have those in series and I could keep doing that. But at this point, I think that it's going to be easiest to keep it just the way it is. So if I look at this thing here, what I'm going to do now is I'm going to say, let's calculate vout and iout now. Why? Because I think it's just the easiest. So now let's go look at our nodes here. So if I look at my first node, note that this is all ground. So if V2 is ground, then V1 must be ground also. So this tells me here is that this is V2 here, and this is V1, and you could see that that's ground. So I know that this is 0 voltage here. So when I'm looking at this process, look at the first thing that I'm going to see here. So the first thing that I see here is that I see that the 6 volt, the 3K, and the 6K are in series. So that means I have a current of 9K that I can calculate. So if I start to look at my currents here, then this tells me here is that I have a current going in this direction like that. And I'm going to call that the current of the 9K. Because there is no current going through this branch right here, right? That current is 0. That means that the current coming in here is also the current of the 9K. So once again here, so if I start to look at this thing, the condition I1 equal to I2 equal to 0 tells us the current through the 9K is the same as current I4, which is that 6K. And another thing that you should note here is that because of the condition V12 in this case is 0, that implies here, so if you look at node V1, you see that the current flows from the ground to a lower negative voltage of vout. So if I come in here and I put a node right here, this node, vout, this node right here has to be negative. So now let's calculate the details. So here we go. So now I'm going to calculate I9K. So if I look at I9K, you're seeing here is that, like I said, the 3, the 6, the 6 volts, the 3K, and the 6K are all in series here. So then that means I'm going to calculate 9IK using Ohm's law. So if I do that, I'm going to see that the current through the 9K is then going to be 6 plus 3 divided into 6 volts. That gives me 2/3 milliamps. So again, that tells me that the current through the 4 resistor is also 2/3 milliamps. Right? So that we now know. So now I'm going to apply the Ohm's law. Again, across R4. So if you look at that guy here, note that I really have what? I have this resistor, which is my 6K, and this is resistor 4. And we know that this node right here, this guy is vout. And we know that this node right here, which is V1, is ground. So now, according to Ohm's law, we know that this current here is this current I4 going through there. So now if I apply Ohm's law, here's what I'm going to see here. Ohm's law then says that that V1 minus V out, and that's 0 minus V out, must be the current. And remember that current is 2/3, has to be what? The 6K times the 2/3 milli. And you can see here that that has to be 4 volts. So then this tells me here is that V out must be minus 4 volts. Exactly as expected, it should be negative. So now what I'm going to do here is I'm going to apply KCL at V out to determine I out. Now, if you look at the op amp here, note that there's a branch right there. So we know that the V out is negative. So that means the current has to be going in that direction for I5. So now, and the way we define this is that the current is flowing in. So let's go look at that. So now if I apply it to that node here, here's what we're seeing. So here's my node. I have my current coming in here, which is I4. I have a current going out, and then I have a current coming in, which is I5. So applying KCL, it says that I out must be equal to I4 plus I5. So I know that this is 2/3 milliamp. And then this guy is coming from the ground, so it's got to be 0 minus 4 divided by 6K, which then gives me 2/3 milliamp again. So then this becomes 4/3 milliamp I out. So I now have both the current and the voltage of the output node. So what I'm going to do here is that I'm going to do this using purely simple circuits, but I'm not going to calculate the current because the current's going to be calculated the same way. The only thing that I'm going to calculate is V out. So here's the simple circuit method. And so let's go look at that. So if I look at this guy, here's my circuit here. So we're not going to use any source transformations. So here, what we're doing is that we only calculate V out. So again, this is 1, 2, 3, 4, and then this guy's 5. So let's start labeling our nodes here. So the first thing that you should see here is that you know that this guy is 12 volts. Because of course this guy's a ground because it's defined that way. And so because that's ground, this is also ground right here. Now, the thing that you want to think about is that if I look at this green node, note that the 2 and the 3 ohm resistor are connected to the same ground. And then we might as well come in here and then put in vout right here. So I know that this guy right here, I have V1 equal to 0 right there, just because I have V2 equal to 0. So the first thing that we should look at here is that resistors 2 and 3 are in parallel. Since they both have the same ground. So now if I look at that thing, what you're really seeing here is that if I look at just this little circuit here, I really have this circuit. So if I look at the sub-circuit, it looks like this. So I have this resistor, and then I really have one resistor here, which tells me that this is 6 parallel to 6, which is in a 3K, and then this guy's a 6K. So I'm going to want the voltage of that 3K. So now I'm going to apply VDR to get voltage of that 3K. So if I do that, that tells me here that the voltage of 2 must be the same as the voltage of the 3, which then is going to be 3 plus 6 into 3 times 12 volts, which I now get 4 volts. So that means here is that this green node is now 4 volts. Now, follow the current, knowing V green is equal to 4 volts. So let me paste in the circuit. So now let's follow the circuit here. So one of the things that I know here is that I know that this voltage right here is 4 volts. I know that that's ground. So when I look at the current, note that the current is doing what? The current is moving in this direction. And because there's no current going through the V1 branch, that same current has to go in this direction like that. So what this tells me here is that because of I1 equal to I2 equal to 0, that tells me that the current of 2 resistor must be the same as the 4 resistor. So now what I'm going to do here is that I'm going to solve for I2 resistor. So if I do that, note that I2, the current of the 2 resistor is then going to be, it's got to be 4 volts minus 0 divided by 6K, which then gives me 2/3 milliamp, which is now the current of the 4 ohm resistor. So now I do the exact same thing. So note, I now know what the current has to be of the 4 resistors. So then I apply Ohm's law again across R4. So if I do that, you could see here is that that current must be, so it goes from 0 minus V out, must be the current flowing through that 4 resistor, which then tells me here that V out gives you minus 4 volts. So this is a slightly different calculation than previously, but it gives you and a different way of actually looking at that. So that was simple circuits. So note that I'm not going to calculate the current because it's exactly as before. So now I'm going to use the node method. So now I'm going to come back in here and I'm going to paste the same circuit as we just did before. So now what I'm going to do here is that I'm going to treat these guys differently here. This node right here, this is V2. And we could see here is that V2 is ground. But this node up here is not ground. This node is what we label V1. So for lack of better language here, I'm going to call this guy VA. So I've now labeled my node. So now I'm going to do the numbers. And here I go. So note that I have how many nodes? I know 12. I know V2. I don't know VA, and I don't know V1. So that means I have 2 nodes. Nope, I have 3 nodes minus 1 source. So that gives me 2 node equations. So I need the node equation for A. I need a node equation for V1. And then I need the ideal model condition. So then that gives me 3 equations, 3 unknowns. V1, nope, it's VA, V1, and V out. So let's go apply it then. So if I go apply it, here I go. So the first equation that I'm going to go after, I'm going to do node A. So node A, I see I have 3 resistors. So I'm going to have 1/6, 1/6, 1/6 times VA. Then I'm going to get 1 mutual. 1 is with the ground, 1 is with 12, and 1 is with V1. So then I'm going to get 1/6 V1 minus 1/6 times 12 is equal to 0. So then I have my second equation, which is node 1, and you can see that I have 2 resistors. So I'm going to get 1/6, 1/6 V1 minus 1/6 VA, 1/6 V out, and that's going to be equal to 0. And then my third equation, which is my ideal model, tells me that I have V1 minus V2 equals to 0. So now that I've written down the equations, note that the ideal model tells you what? It tells you that V1 is equal to 0. Okay, so that's an important condition right here. So if I know that V1 is equal to 0, I can now come back and kill off that term, kill off this term. And so what this really means here is that I only have really 2 equations left. So you could see that the first equation gives me 1/6, 1/6, 1/6 VA. And then this guy, if I put it to the other side, I get that condition. And then if I look at the second equation, note that this really tells me that I get VA plus V out equals to 0. So if I compute that, I find that I get V out equal to minus 4 volts, which is exactly what we computed before.